Hi all, this is Dr. Shanthi, Professor, EC Department, RMK College of Engineering and Technology. In this video, we are going to study structure of atmosphere, which comes under Unit 5 of structure of atmosphere. Now, when you look at the diagram, immediately following the Earth's surface, up to 15 kilometers, you have what is called as troposphere. Right, then immediately following the troposphere, you have what is called as tropopause and stratosphere. Extending from 50 to 450 kilometers, it is going to be ionosphere, and ionosphere is also composed of various layers like D layer, E layer, F1 layer and F2 layer, right? And the outermost region is going to be your outer atmosphere. So broadly classified, it is troposphere, ionosphere and outer atmosphere. Now let us see let us discuss about structure of troposphere. Right now, in polar latitudes, the troposphere will be at a height of 8 to 10 kilometer, and it is 10 to 12 kilometer at moderate latitudes, and it is 16 to 18 kilometer at the equator. On an average, the troposphere is extending up to 15 kilometer from Earth's surface. The actual height is least at poles and maximum at the equators. Now this is what is told in the first point. It is up till 8 to 10 kilometer in polar and 16 to 18 kilometer in equator. That is what is told in this point. The composition of a troposphere remains approximately the same as that of the surface of the Earth. The entire belt is called as troposphere or region of change. In troposphere, the percentage of gas components remain constant with increase in height, but water vapor components sharply decrease with height. In troposphere, the temperature decreases with increase in height and falls to a minimum of minus 68 degree Fahrenheit. At the top of troposphere, we have what is called as tropopause and ends at the beginning of stratopause, or which is the region of calm. Above a certain critical height called tropopause, the temperature remains uniform through the narrow belt and begins to increase after that. In stratosphere, no intermixing due to air currents takes place, and the composition of atmosphere varies with height and stratification begins. Now, refractive index of the troposphere at the surface of the Earth is just 0.003% greater than unity. That is, you have n is equal to mu minus 1 into 10 power minus 6, and n is excess refractive index over unity in millions. Troposphere is an inhomogeneous dielectric medium whose refractive index varies with the height and so also the velocity of wave propagation. Now comes to structure of ionosphere. Immediately following troposphere is ionosphere. As I told you, why this is called as ionosphere is you have what is called as ionization taking place in ionosphere. What is meant by ionization is nothing but the charged particles there. That is, they get ionized by the sun rays, and you have positive and negatively charged ions formed. The upper part of atmosphere from 50 to 400 km, where ionization is appreciable, is known as ionosphere. It consists of several layers of electrically charged gas atoms called ions. The ions are formed by the process called ionization. The ionization depends upon sun and its activity. The most important ionizing agents are ultraviolet rays, alpha rays, cosmic rays, and meteors. The wave transmitted towards ionosphere can be received back on the Earth's surface due to the combination of reflections and refractions. The wave received through the upper part of atmosphere is called as sky wave, and the mode of propagation is called ionospheric propagation. A long distance communication is achieved by using sky wave. The amount of ionization in the ionosphere varies greatly with the amount of radiation received from the sun. Solar radiation acting on different composition of atmosphere with height generates various layers of ionization. There are basically four layers: D layer, E layer, F layers. You have F1 and F2 layer. and this ES layer is a sporadic layer, right? Now, why I call it as four layers is basically D layer, E layer, F1 layer, and F2 layer. Now, this diagram shows the layers of ionosphere. So first is a D layer, 50 to 90 kilometers D layer. Then 90 to 140 is E layer. 140 to 250 is F1 layer. 250 to 400 kilometers F2 layer. So these are the various layers of ionosphere. Now this diagram, just one another view showing the various layers of ionosphere, right? So D region, E region, F1 region and F2 region, and the distance once again is shown here. Now what happens during day and night? Now look at the diagram here, electron density and height above the earth. Now during day, what happens here is you have a D layer, you have E layer, F1 layer and F2 layer. You have four layers here during daytime. So four layers are visible during the daytime. But what happens at the night? Look at this diagram. You can see only one E layer and one F layer. Both F1 and F2 layer combine together to form F layer, which is called as Appleton layer. E layer becomes, you call it as E layer or Kenley heavy slide layer, and D layer all together vanishes at night. Now let us study about each of the layer in detail. D layer is the innermost layer located 50 to 90 km above the Earth's surface. This appears only during the daytime and is responsible for microwave attenuations. During nighttime, it does not appear due to ion recombination. The recombination rate is highest at night and degree of ionization depends on the altitude of sun, resulting in vanishing of D region at night. And the electron density ranges between 10 power 14 to 10 power 16 ions or electrons per centimeter cube. D layer can be used for very low frequency and low frequency communication. Medium frequency and high frequency will have little absorption in D layer. D layer is also known as absorbing layer for high frequencies. Its critical frequency is about 100 kilohertz. Now coming on to E layer is located at 90 to 140 kilometer, and in this region ionization is due to X-rays and ultraviolet rays. The electron density ranges from 10 power 5 to 4.5 into 10 power 5 cubic per meter in the day and 5 into 10 cube to 10 power 4 at night. The ion density is constant during daytime. Maximum density occurs at 110 km from Earth's surface. It is also called as Kelly heaviside layer, named after the two men to propose its existence. Critical frequency ranges between 3 MHz to 5 MHz. This layer is most useful for long distance communication. Then you have one layer called as sporadic E layer. Right now, I call it as sporadic? It is formed by clouds of intense ionization. This layer is quite irregular. That is why I call it as sporadic, and hence the name sporadic. It occurs in the form of clouds varying in size from 1 kilometer to several hundred kilometers across. It may appear anywhere in the height range of 90 to 130 kilometer with normal E layer. It can support radio wave reflections from 25 megahertz to 225 megahertz. It may be observed in both in day and night hours and may in any of the season in the year. That is, in polar region, this layer occurs during night and in equator regions in daytimes. It is a very thin layer of high ion density. The electron density is 10 times greater than that of normal E layer. This layer is not very important for long distance communication, but sometimes it results in good reception, right? See here, due to the presence of sporadic layer here, you will have M-type reflections from resulting from the ES, that is sporadic layer, right? So the signal from here gets reflected from F layer, and rather than reaching the earth receiver directly, it undergoes M-type reflections because of the presence of sporadic layer. Next is F layer. F layer is known as called as Appleton layer, located at 140 to 400 kilometer. Average height is 270 kilometer, and ionization is extreme here. The topmost layer of Earth of the ionosphere. It is always ionized irrespective of hours of the day, seasons of the year. F is responsible for high frequency radio communication over long distances. During night, F1 and F2 layers combine and form one layer called F layer. During day, F region splits up into two layers called F1 and F2 in low latitude stations throughout the year, and only in summer in high latitude stations. Now coming on to F1 layer. F1 layer is 140 to 250 km above the surface of the ground. Average height is 220. Electron density is 2 into 10 power 5 to 4.5 to 10 power 5 cubic meter. Critical frequency is between 5 megahertz to 7 megahertz. F1 layer is formed by the ionization of oxygen atoms. Although some of the high frequency waves are reflected from F1 layer, but mostly penetrated and is reflected by the F2 layer. Hence, the main effect of F1 layer is to provide noise observation of high frequency waves. Now, F2 layer from 250 km to 400 km above the Earth's surface during daytime and falls 300 km at night time, where it combines with F1 layer. The electron density is 3 into 10 power 5 to 2 into 10 power 6 per cubic meter. The critical frequency range is between 5 megahertz to 12 megahertz. The ionization in F2 layer is affected by Earth's magnetic field. Ionizing agent in this layer is UV and X-rays. F2 layer is the most important reflective medium for high frequency radio waves. Now coming on to the outermost region or outermost atmosphere is the G region. Outer region of ionosphere at a distance more than 400 kilometers is said to be G region. This region usually occupies the radiation belts consisting of charged particles trapped by terrestrial magnetic field depending upon magnetic lines of force. Thank you.